My name is Bart Krop, and I'm a curator here in the museum, and I will be moderating this lecture today. We have a young PhD student, researcher. Student sounds so. PhD researcher. I have to pronounce it correctly. Noemi, right?
Very good.
All right. Noemi La Bella, and she will explain us today, because it was a personal question of me, why is this image of the black hole orange and yellow, and why isn't it blue, for example? So I hope you can enlighten us. The floor is all yours.
I hope so. Thank you so much. Thanks, Kius, for inviting me here. It's a pleasure to talk about the image of the black hole. And to answer to your question, why it's red and not blue, why it's not green, why yellow, we don't know. We don't know which light actually emits, because it doesn't emit at visible light. If you go there, I don't suggest it, but if you go there, you don't see anything, because this is not visible light. These are radio waves. But I'm going to explain it right now. So in this lecture, I will talk to you about how we did take the first image of the supermassive black hole in M87 galaxy. And then I will tell you how we did take the first image of the supermassive black hole at the center of our own galaxy, the Milky Way. And as I mentioned, the light that is there, the photons around the black hole, they do not emit in visible light, but radio waves. So we need radio telescopes. And I will explain you how the radio telescopes work. But actually, we do not need one single radio telescope. We need a collection of radio telescopes that are around the globe. And this is the Event Horizon Telescope. Then, of course, I will talk a bit about my own work and the fact that we are a collaboration. We are 300 scientists, and everything I'm going to explain you is actually a work from this incredible collaboration that I am part with. Okay, so we really like to start with this movie. I hope it works. Maybe I should. It's not working. I will try again. It's a very nice movie, so it's not, it was working before. Okay, finally. Okay, we go to the center of our galaxy, the Milky Way. So from the Earth, from actually ALMA telescope that's in Chile, we go inside the center of our own galaxy. And you already see that we need to cross a lot of materials. There is gas, there is dust, there are stars. So it's very tricky to take an image of the black hole, because we need to correct all the spurious information that we can have. And then, of course, we go to the center, and we have our picture, the first image of the supermassive black hole at the center of our galaxy. But before talking about that, I really would like to explain you a bit about the black hole, how we take an image of the black hole. First of all, this is M87. M87 is the supermassive black hole that is located at 55 million light years from us. And it has a mass that is 6 billion solar masses. It's a huge supermassive black hole. And you can think like, okay, it's a very massive black hole. How it's possible, it's so tricky to see it? And also, supermassive black holes are like the brightest object that we have in the sky. So how it's possible that such a bright object and also supermassive is so complicated to see? Because it's very, very small. Its apparent size on the sky is very small. So to give you an idea, we have that the apparent size of this black hole on the sky, it's about 20-40 microseconds. We call this angular resolution, which is the ability of a device to detect two single features. Now we have this black hole that emits at 1.3 millimeters. 1.3 millimeters is radio waves. It's not visible light. So we know the apparent size on the sky. We know that this angular resolution should be 2040 microseconds. We know also the observing wavelength, so we can estimate how big should be our telescope to observe and catch the image of the black hole. How big should be this telescope? Earth-sized dish. So it should be a dish that is big as the Earth, which you can think already that's quite tricky to build for funding reasons and for all the other reasons you can think about. And to give you an idea how high should be this resolution to catch this image, it's like to have an orange in the moon and you want to see it by eye. So this is the comparison to understand how powerful should be our telescope to actually catch the image of the supermassive black hole. Okay, we understood that we need a Earth-sized dish, which is impossible to build. This is why we create a virtual Earth-sized dish. So we connected different telescopes in the world to have the same resolution that we have with a virtual Earth-sized dish. And we have these telescopes that are spread around the world. In particular, in yellow, you can see the telescopes that observed in 2017 and that actually made it possible to have the first image of the supermassive black hole. There are also in green other telescopes because the EHT is growing. This telescope is growing. We have more telescopes that are joining our observation, and so we can have better reconstruction, better images. Now, how it works, the observation with this telescope? We have 2 weeks where we can observe. And this telescope, actually, we didn't build these telescopes. They were already there, and we borrowed them. So we asked the people if we can perform this observation. And we have 2 weeks to actually trigger the observation. But we don't observe for 2 weeks in a row. We only observe for 5 days, because we have to store this data in our drive, and we have a limited space, of course, where to store our data. So how we can decide in 2 weeks which are the best 5 days to actually observe? And the point is that we decide this in base of the weather condition. Weather is very important, because if we have a strong wind, you can imagine this antenna, this parabolic dish that actually move, and we cannot observe anymore. So we have a server, online server, that can actually see the weather condition at each telescopes. So we can monitor the weather at these telescopes. And we can decide when is the best time to actually observe. Now, a funny part here is that last month I was in one of these telescopes. I was in 3,000 meters in Sierra Nevada, Spain, and I was observing there. And I thought that would be nice to show you how it is actually to be in a radio telescope. So there is this video that I hope even this time it's working, but it's not working. Oh, yes. On the top of the mountain, I was there. This is Pico La Valeta. It's a dish of 30 meters of diameter. And the view was amazing. I was also excited, and of course, it's not very clear. But yes, it was an amazing, really, experience to be there. And a funny thing is that how to reach a radio telescope, I also didn't know. And so the people told me, you know, there will be a bus at 7 a.m. in the morning. So I was there ready for a bus. I found a car, but, you know, bus, car, it's almost the same. Then we stop, and they will say, there are other 2 transportation for you. So a gondola for the skiers, and there's no track. So with the snow truck, we went up to the mountain and we reached the telescope. And for me, it was, what? Of course, I didn't observe alone. There were other early career members as well. You can see here the photos, and you can see already from the photo, the faces are from different countries, because the HD collaboration is a global collaboration. Another funny thing is that, we have this shift during night where we can observe. And you have to wake up during the night at 3 a.m., 4 a.m., and observe. And after 5 days in a row, you started to be tired. So one day I was very tired. I text my mom, "Oh, Mom, I cannot do it anymore. I'm very tired." And she was like, "It's amazing. You're looking at the star. You're looking at black holes." That's what I was looking at. 4 a.m. in the morning, I was actually looking at 5 different screens, because this is how we do radio observation. We actually look at the screen, at the signal that we register. Okay. But let's go back to the explanation. What is a black hole? A black hole is a region of the space-time where gravity is so strong that nothing, not even light, can escape. What does it mean? It means that gravity, we know gravity, is not this abstract force that we can imagine. Gravity is actually curving this that we call space-time. It curves so much the space-time that the light around it is also bended. And for an object that is massive as the black hole, that's very massive, you have that it creates a boundary that is called the event horizon, where nothing can escape from this event horizon. So this comes from Einstein, of course. Einstein, the theory of general relativity in 1916. It says actually it is, that gravity curves the space-time. And this depends also from the mass of the object. So more massive is the object, more this space-time is wrapped. And so the light around it will be, of course, bended. This is the idea that we have for our image. It is an explanatory video here, where you can see the light that is bended when it passes close to the black hole. And closer it passes, more bended it is. And of course, we have a lot of light rays. And all these light rays can be thought as pixels in our images. And what we see at the end is the projection of these light rays that are bended by the event horizon. So this is what we observe. This is the image of the shadow of the black hole. Now, if you are an observer, you can notice actually that this image is very symmetric, it's very uniform. But what we have even in this museum, the image of the black hole is more bright on the bottom. So why this is? Well, this is due to the Doppler effect. Now, I don't know if you remember from your studies, I heard someone from science, but if not, it's something that you experience every day. It's basically when, for example, there is an ambulance that passes you, and when the ambulance approaches you, you hear the sound louder. And instead, when it goes away, you hear the sound, of course, less louder. And this is when the ambulance approaches you for a stationary observer, you have the sound that is a higher frequency. And when it goes away, instead, it's a lower frequency. This is the same for the light. So if you have the light that is approaches you, you have this an higher frequency, and we call this blue shift. When instead the light is going away from you, this is a lower frequency, and we call this instead red shift. That is this one. So what happens in the black hole is that the black hole rotates. So when the material is approaching to you, You see it, of course, a higher frequency, so brighter than actually it is when it is going away from you. What did you think about to take the shadow of a supermassive black hole? Heino Falke. Heino Falke is actually my supervisor at Radova University. And if I was the first one that thought that we can catch the shadow of supermassive black hole. And you can see from here that he published this paper in 1999. And it says exactly this. It says that for a distance observer, the event horizon casts a relatively large shadow with apparent diameter of 10 gravitational radii that is due to the bending of light of the black hole. And then it says also here, it says, we show, because they did a simulation in this paper, that the shadow of a Sagittarius star may be observable with a very long baseline interferometry, this is the EHT, at sub-millimeter wavelengths, so at 1.3 millimeters, and hence there exists a realistic expectation of imaging the event horizon of a black hole within the next few years. It wasn't really next few years, it was 10 years later, but it happened. We actually did it. We actually have the first image of the shadow of the black hole. And of course, what thought Arno Falke was, together with other collaborators, we need scientists, we need institution, we need money, we need a lot of effort to make it possible. And this is actually the Event Horizon Telescope collaboration. The Event Horizon Telescope collaboration is, we are 300 scientists in 20 countries, 60 institutions, and 80 millions. Well, 80 millions for a 4 pixel to 4 pixel image. So the image that you send by phone is quite expensive, yeah. But anyway, to give you a representation of the effort to make an image of the black hole. Now, I would like also to show you some picture of my own journey in this collaboration. So we have usually some collaboration meeting when we try to be all together. And the first one that I could join was in 2022 because there was the pandemic. And it was in Granada. You can see already from the photo the amount of scientists that there are there. And we had a second one that was in Taiwan in 2023. And the funny part of the EHT collaboration is that these scientists are not only people from physics or astrophysics. There are engineers, there are people that know better electronics, because we need all the kind of information. We need from theory, from observation, from imaging. Then there is the Radboud team in Taiwan. This was my first talk to a science audience. I was very excited because indeed there was the COVID, so it was impossible for me to communicate. The Dutch team after the Sagittarius Star press release. This is another photo of Heino and Monika Moschit-Broska. She is a professor at Radboud. She gave a lot of contribution in the theory part of the Event Horizon Telescope collaboration. And this is again the Radboud team after the Sagittarius Star press release. Okay, I will try now to explain how we make an image of the black hole. So I hope we can follow me in this journey. We have the first step, that is observations. Then we have what we call correlation, I'm going to explain this, calibration, imaging, and simulation. And as you can see from here, we start with observations that are petabyte of data. And then we arrive to imaging kilobyte. So from petabyte, we actually arrive to an image of kilobyte that you can send by phone. So I'm going to explain how this is possible. And also another step that is very important, these are simulations, the theory. So we not only deliver an image, we also do all the theory part and all the simulations to actually compare our results with the theory. Okay, let's start with observation. So, light actually can emit different frequencies. We have gamma ray, X-ray, ultraviolet, visible, infrared, microwave, radio. What we can actually see is only the visible light. So if you have a telescope at home, for example, you can see only the object, the celestial object, that emits invisible light, like stars, planets. Or if you are more professional astronomer, you can build this optical telescope in a mountain, and you can see, again, planets, stars, but even galaxy, all the kind of object that emits at this frequency, the visible light. But we have also other frequency. We have gamma ray, X-ray, and as you can see, these are stuck by the atmosphere. They cannot pass through the atmosphere. Thanks God, because we don't want the gamma ray or X-ray that hit us, of course. But so they cannot pass through the atmosphere. And then there are the radio waves that can reach the Earth. So we can build a radio telescope, and we can actually detect the radio waves from the black hole that comes to us. Now, all these other frequencies can show other characteristics, other features of the celestial objects. So this is why we have the satellites. We have other telescope in space that we launch this telescope in space, and so they can observe these other frequencies, and we can detect other information. And this is actually what we do also with the EHD collaboration. So we have the EHD, where we observe at actually radio waves with all these radio telescopes around the globe. But we have also other telescopes, these space telescopes, that can actually detect other structure. For example, this is still the M87, is this one, but we can see the jet of M87 and extended emission, because we observe, in this case, an X-ray. But if we want to see the black hole shadow, we need exactly 1.3 millimeters, this radio wavelength that you can see here. How the radio telescope work? How it does work? Well, we have the poor light wave that is bent and passes through the entire galaxy and then reach the atmosphere and go through the atmosphere, and then the incoming radio waves from distant celestial object can reach this parabolic dish. This parabolic dish, it actually reflects the light. We have a primary parabolic reflector surface. It goes to the subreflector, and then it focuses the light rays in this called the feed horn. It's not moving? Okay, the feed horn here. Which this feed horn, it's like horn that make it possible to have the radio waves that go to the receiver. So basically, the idea of antenna is to convert the radio waves into signal. And then we have to amplify this signal because it's very weak. And so we have this receiver, this amplifier, and then we record the signal in our drives. There is a problem with the EHD, and the problem is due to the Earth curvature. The Earth is rounded. So, when we have our source that emits this radiation, you can see already that it's one telescope, but not the other one, because the Earth is rounded. So the signal will arrive first in one telescope and later in another one. So we need to freeze the signal in order to later combining it. So we have a precise atomic clock that freezes the signal, And then we collected the signal in all the telescopes, and in a second time, we can correlate it. So we have a supercomputer, two big supercomputers. One is in US, and the other one is in Bonn, in Germany, where this supercomputer basically realigned the signal because of this time delay that we have because of the curvature of the Earth. And the funny part here is that petabyte of data cannot be sent by Wi-Fi. We need to ship them by plane. And the problem is that we have one of the telescopes that is South Pole, and we don't have flights so often to South Pole, so we needed to wait 6 months to have the data from South Pole that actually reached these two observatories. So it's a long journey for the data. So, okay, we align the signal, but what this supercomputer do not do is to consider the atmosphere. And the atmosphere is important. Atmosphere is important because it's true. The radio waves can pass through the atmosphere, but the atmosphere can scramble the quality of our image. So we need to correct for this noise. In particular, we have that the distance between two telescopes is called baseline, and this gives us the resolution of our ray. And we use this pair of telescopes to actually calibrate the data, meaning to correct for the effect of the atmosphere. Effect of the atmosphere, effect of the antenna itself, we can have receiver noise, we can have so many noise. So actually our data are very noisy. And this is an example of plot that we have when we do this process. And we have that before this calibration step, we have a very noisy data set. So what we do is to average the data, to have to increase the signal to noise. But if we average the data like in this condition, we actually decrease the information, we don't have more information. So we needed to clean the data from all these factors, and then we can average the data. Indeed, you can see from here that actually we have a more clean information. Now, this process that I described so far, correlation, calibration, how long this could take? 1 month, 2 months of work? 3?
How many percent of your data is noise?
Well,
Is that 90% or?
yeah, no, 90%, I think 80% could be. But then, of course, we clean it. Yeah, let's say,
What are you wiping out?
yeah, let's say 80%.
Don't throw everything away.
Yeah. So, you know how long it does take? 1.5 years to actually clean our data. And this is a cycle, because what we do is basically to have this correlation where we combine the signals. Then we have this pipeline that were built by dedicated team that correct for the correlation errors, but also atmospheric errors. And then we have a data validation team which check the quality of the data. And if the data are not good, go back to the first step. And this was for 1.5 years. Okay, but let's say that now we have the clean data set. Okay, we can start to image our black hole. Imaging, what does it mean? This is actually very complicated, but I will try my best to explain it. So, I told you before that the distance between two telescopes is called the baselines. That is the resolution of our ray. But what we have is, we don't have an image, right? We work with signals, with data. So we have this measurement plot, and we have that two single telescopes give us only 2 points. What kind of image we can detect with 2 points? Ideally, we would like to have the entire Earth covered by a radio telescope. So in this way, in our measurement plot, we can have a filled disk, a lot of information can help us to recreate, to reconstruct the image of the black hole. But of course, this is not the reality. The reality is that we have just a few telescopes, but also we use the rotation of the Earth. So with the rotation of the Earth, with the combination of telescope, we can actually reconstruct our image. I know that maybe still it's not super easy to understand how we can go from this measurement plot to the image. I will try to explain. So it's called Fourier transform. Maybe someone of you know, maybe not. But it's a magical tool. It's a very magical tool where we can go from this frequency domain, we call, because we are not in the imaging domain. We have only data at certain frequency. And then we can pass it through this imaging domain. So we have this equation, this magical tool, that can let our algorithm to pass through these measurements to an image. There is another issue. And the issue is that, actually, as I showed before, the EHT is a very sparse array. We have a few telescopes in the globe. So there are a lot of possibilities. There are a lot of images that can actually fit our data. You can think this like a puzzle. If you have a puzzle and you have only a few pieces of the puzzle, it can be a bit everything. More pieces you add, more easier it's for you to understand which is the image. And it's the same with the telescope. More information we have, easier it is for us to understand which is the image it is. So there are an infinite of possible images consistent with our telescope measurements. So what do we do? So we created these imaging algorithms, and what they do is to find the most likely image, because we have an idea how the black hole look like. And we know from the theory. This is a theoretical simulation that I will explain later, but we have theoretical simulation can tell us how the black hole look like. And so in this algorithm, we can do the Fourier transform. We can pass it through the measurement set with the image, and we can select the image, the most likely image that fit our data. Okay. You can think also, this can be a computer-biased process, or can be a human-biased process. This is why we have 3 different algorithms and 4 different teams. So for the first image of the black hole, there were 4 different teams in 4 different places of the world, and they were trying to reconstruct this image with this method. So they had 3 different methods to use. They didn't talk each other, and they obtained these 3 images. So we have the 3 different methods, and you can see that the image is pretty similar. This means that actually we are looking at the shadow of the supermassive black hole. And this is really an incredible discovery that was made. But let's go now to another part that are simulations. Because we obtained the image, but it's also important for us to understand the physics that there is behind. So this is also a video that was created from Jordi Delvar at Radboud that represents this kind of simulation. I am an observational astronomer, so I'm not doing this stuff, but I can explain you that the idea is to put all the kind of physics, plasma physics, magnetohydrodynamics, into a computer, an algorithm, and it creates this simulation. So you can think a theoretician, maybe someone that does the equation by paper, but nowadays you can put this equation in an algorithm and create our simulation, and this can tell us how the black hole look like, but also the physical parameters. For example, the spin of the black hole, the rotation of the black hole, or the size of the event horizon. We can have a lot of information from theory. And this is a very important step for us, because we need to deliver also the image to the science community, right? We need to have information of the physics, not only the image of the black hole. Okay, let's go now to the supermassive black hole at the center of the Milky Way, Sagittarius star. Sagittarius star is smaller. It's 4 million solar masses smaller. And it's closer to us because it's at the center of our own galaxy. It's located at 27,000 light years. This gives us an angular resolution of 50 microseconds. So, okay, it's a smaller black hole. It's closer. The angular resolution is even bigger. Why came 2 years later this image? Why do not image first Sagittarius star that's closer and smaller? Because the problem are two. Yes?
Is this billion an American billion or a European billion?
Billion?
Million is the Sagittarius alpha, and 87 is the 6.5 billion solar masses.
It's 10 to the 9.
10 to the 9.
Okay. Okay. So there are two main problems for imaging Sagittarius star. And it is because it's located at the center of our galaxy, it means that we have a lot of materials because we are located here. So what happens that we need to correct for what we call the scattering. Because we have this light from the center of the black hole that have to cross all the materials that there is between us and the center of the galaxy. So the light can be deviated. And so we needed to correct to this factor, otherwise it scrambles our image. And this is the first problem. The second problem is that Sagittarius star is quite variable. As it is smaller, it rotates faster. You can imagine these two black holes with dogs. So we have a supermassive black hole that is represented by this dog that's very massive and lazy. It just doesn't want to move. And then we have a Sagittarius star that's a puppet that when to reach its tail constantly is moving. And we are looking at this small puppet from a window, and it's also raining. So it's much more complicated to take a picture of this dog than the massive one. To give an idea how fast Sagittarius star is rotating, this is another simulation that was made. So you can see here M87 and here Sagittarius star. So what happens is that we observe Sagittarius star is constantly moving. And we're like, oh, wait, one image. No, we can't. So how we can create one single image of a Sagittarius star if it's constantly moving? We don't. We don't create an image of Sagittarius star. 10,000 images of Sagittarius star. This is what we do. Now these are simulation. We actually have all the images that we reconstructed. And how we can decide which is the true image that represents the black hole at the center of our galaxy? We needed to develop new algorithms, even more, because what we had for M87, that was a massive stable object, we couldn't apply for Sagittarius star, that is instead a very variable object. So after developing all these new algorithms, we also had this technique that's called clustering. So we clustered the images that had similar features. So all the images with a similar characteristic, we clustered in one cluster, then we averaged, and then we did this with another cluster, and so on. And at the end, what we had was 4 clusters. And these are the 4 clusters that we at. You can see already that 3 of these clusters show similar feature, the ring-like structure of Sagittarius A. Only one did show a very clear ring-like structure. But after all the effort that we made with all these 10,000 images and all the simulation we made, we were pretty confident to show the first image of the black hole at the center of our own galaxy, Sagittarius A. Okay, I hope you followed me in this journey. Now the question is, what is the future? What is next? And I will talk to you about a bit about my own work, because this is my first paper that I published a few years ago. And the future is to have more telescopes, because more telescopes means that we can reconstruct better our image. And also, we want to generate movies, because you saw, right, Sagittarius A is moving very fast. And if we create a movie, it's much easier to understand how the gas flow around the black hole. So in this paper that we published, basically we consider, okay, one letter went away, but we consider a telescope in Africa. We consider a telescope in Namibia. Namibia is a very good site, and in particular, the idea is to build a telescope on the Gamsper mountain, that is 2,000 meters. And in this paper, I wanted to show the impact of this telescope in producing movies of Sagittarius A with the Event Horizon telescope. And indeed, what we saw is exactly that, in this movie here, that we can reconstruct a variable feature in our black hole. This is a simulation, it's not reality, but we can reconstruct an image of a movie, with higher quality with the additional African telescope. Now, building a telescope in Africa is quite complicated, because in the Gamsper mountain, there are no roads. So we need to build everything. And I wanted also to show you this because it's a huge effort of the Dutch community as well. First of all, we see again Heino Falke. Sarah Markov is from Amsterdam, and Rob Fender is from Oxford. And they are the PI of this project. And you can see here that says this journal, astronomers receive ERC a grant to make colorless movies of black holes and build new telescope in Africa. This was the first grant we had, and then also the NWO grant. So the Dutch Research Council grant 3.4 millions to create this telescope in Africa. And of course, it's a lot going on, even with politics, because building a new telescope involves a lot of factors. And actually, I think the vice president should be here next week. So there is continuously connection with the Namibian. And another important thing is the NOVA Mobile Planetarium. This is also a Dutch program. And there is this NOVA Planetarium that is going from school to school in Namibia to motivate the young scientists or the young children. And I recently heard that there are students in Namibia that want to go to study astronomy because they know there will be a telescope there. And this is so nice. I produced these simulations just thinking about movies of black hole. I didn't think it's that actually this can have a social impact, and it's so nice to see how people can be enthusiastic about a telescope in their own country. Another thing for the future, space. We want to go in space. We want to bring a radio telescope in space. This is actually something that Freek Rulof, who was a PhD candidate at Rado University, says, and he also published a paper about it. And it says this, it says, there are a lot of advantages to using satellites instead of permanent radio telescope on Earth. as with the Event Horizon Telescope. And then it says also, in space, you can make observations at higher radio frequencies, because from Earth, these are filtered out by the atmosphere, as we saw before. The distance between two telescopes in space is also larger, which means higher resolution. This allows us to take a big step forward. If we have a telescope in space, we can have 5 times the resolution that now we have. So it would be a huge step forward. But as I saw a bit how the things are going with the African telescope, I think will be a bit complicated. So it's not the next year, but probably in the future this will happen. And yeah, I think I'm done. Thank you so much.
Thank you very much, Naomi, for your wonderful presentation and taking us along with your journey. Not only your scientific journey, but also those amazing trips towards the top of the mountains with these snow tracks, for example. Thank you very much. We have time for a few questions. Just one household rule. I will come to you with the microphone. Otherwise, the people who are watching the stream can't hear you. So you were the first, and then you.
Black holes are non-visible, but you have to aim at something in order to receive the best signals. Do you know the whereabouts of black holes in the sky or in the space? And when not, how do you aim to get the best results? Or is there no question of aiming?
So I'm not sure if I get exactly the question, but thank you so much. In case, please let me know. So we did the images of supermassive black holes because we can catch the shadow, we can have the resolution. But there are other black holes in the sky, of course. But for example, much smaller, because they are not supermassive. So our aim was to catch the shadow of supermassive black hole, where you can learn a lot of information from them. Because from an image of a supermassive black hole, we can learn a lot about the physics. So for example, gravity. We can learn about the gravity force. And so it's not only the image itself, it's the physics. The aim is the physics. And also, I have to say that all these complicated image algorithm that we saw, we developed this for black holes, but you can apply this for medical reasons, for other reasons. So there are a lot of aims behind all this work. It's not even only the single image that we saw.
Yeah, but I think if I may try to explain your question, because I was wondering the same. You know, you have in this project you have combined 8 telescopes from around the globe, and what I imagine is that there is a black hole over there.
Yeah.
So, but there could be a black hole over there as well. So, how do you decide to point all these 8 telescopes to that point and not to that point in the sky?
Okay. Yes. This is again for the apparent size that we have. So there are closer black holes, but the point is that we cannot observe this with the Event Horizon Telescope because they are smaller. So we don't have the resolution to see them. Instead, the only 2 supermassive black holes that we can observe are M87 because it's gigantic, and Sagittarius A because it's closer. And so the combination of these 2 factors give us an apparent size that actually we can catch with the Event Horizon. If we go to the space, for example, if we go in space in future, we can have a high resolution and we can observe other black holes.
There's a question over here.
Why do you use this specific wavelength of 1.3 millimeters? Is there a specific reason?
Yeah, it is because the radio, the light around the black hole emits at this radio wavelength. So if we want to see the shadow, that is this light that is banded around the black hole, we needed to actually observe at 1.3 millimeters. Yeah. And it's also true that one thing that we want to do in the future is maybe observe a higher frequency, so a lower wavelength, to have a better resolution. But this is, for now, the best.
And that is for both of them?
But,
For both of the black holes?
yeah, sure. Yeah, both of them.
Are they over there? Yeah.
Thank you for the talk, really nice. I have two questions actually, one shorter. There's also the James Webb Telescope.
Mm-hmm.
Can you use that for your research?
Can I?
Yes, please.
Okay, James Webb, it's the follow-up of Hubble. So I actually showed an image here. Let's go back. Here, where there are all the other telescopes. And this is an image of a Hubble Space Telescope. And so we can see the visible light. So we can use it for observe other parts of the telescope, the supermassive black hole. Not the shadow, but other, for example, stars or other information that are around.
Okay,
So
very clear. The second question is maybe a little bit more broad about your work as a researcher. So the black holes were once a theory, I think in the 1930s or earlier, and then it took until 1970 until it was proven. Maybe I'm wrong but it took a long time. Is there maybe a new phenomenon in the universe, which is still a theory now? What you are excited about, what may be proven in the future, near future?
This is a big question. I'm easily excited, as you could see from the observation. But yeah, for example, something that is still not tested yet by observation is the Hawking radiation. The Hawking radiation is basically this idea that we have radiation from the black hole. We can actually see the black hole. So there is one particle that go away, one particle that go inside the black hole. So we have this evaporation of the black hole. And there would be maybe something, I don't know how we could observe it, but this can be something that can be tested. About EHD, I think it's also nice to think about, I didn't show it, but we did a lot of studies of magnetic field. And this is maybe more complicated, but at the same time gives us a lot of information. The magnetic field, to understand the polarization. This light is polarized, it gives a specific, goes in a specific direction. So there are many, I think, things. And about black hole, indeed, it's amazing. I'm also amazed how it's possible that from theory, there was, I think, in 1990, I think, Karjowski was the first one that detect the first radio waves from the center of the galaxy. He didn't know what a black hole. He didn't know. And then now we have an image of this black hole. So it's impressive. And I'm also looking forward. I cannot really answer what are like all the questions we can answer, but I am very happy to be part of this journey, whatever it will be.
Thank you.
I think one of the new challenges is dark matter. But not about that. You explained the difference in brightness on the picture by Doppler. The light comes at the speed of light, and if the black hole is coming towards you, then it should be bluer, and if it goes away, but it's only on one side. So is that because the rotation of the black hole, that one side delays the light?
So it is true, it's only one side because it's also the inclination of the black hole. This is a black hole that is like hadron. You're looking at this, imagine this is the accretion disk. You're looking this like this. So you see, boom, the light that is coming to you in this way, and the other one is dimmed. So this is why only from one side you have the brightest one, and the other side you don't. If you look maybe on this way, maybe you can see the light is coming you on both waves. But in this way, you have only the light that is approaching to you that is brighter.
Okay.
We have time for one more question. If not, oh, okay. Just in time.
I was wondering about, you told us there's different algorithms that you use to get the images in the end. Usually if you have an algorithm, then you have fed in like images before to come up with the algorithm that will give you the images that you end up with. So you didn't have images before that you could fed into your model to in the end build it. So those were probably theoretical. But maybe you can explain how you did that.
This is a good question. This is a really nice question. We actually have them. What we do are called synthetic data, fake data. So what we do is, it's like what I did for this work, right? For the African telescope. We don't have the African telescope yet, so how could show the movie of the African telescope if it's not there? So what we do is to generate fake data called the synthetic data, where we have the exactly process of the EHT, so observation data, imaging perfectly, and then so we have an hypothetical image that we can use in our algorithm. So we need a lot of tests in that sense.
Thank you very much. Can I have a large round of applause for our speaker today? So, and I would like to thank you on behalf of the museum for your attention here today. And hopefully we'll see you all back next month in the last lecture in this series about black holes. And if you haven't seen the exhibit yet, go and have a look. You can also find one of those disc packs that you were carrying around all over the globe. So, thank you very much and enjoy your weekend.